So the presenter for this paper is going to be Skip Crilly. Most of you here know him as the fellow who gets us into the 40-foot telescope and gives training on it and hands-on. But uh, uh, Skip has been building radio telescopes since the late 1960s, and he built his first radio telescope in the Philippines, where he grew up. After college, Skip worked for Hewlett Packard for 27 years in wireless test equipment, research and development. He then worked for several wireless equipment companies. And since 2014, he's been a volunteer engineer at the Green Bank Observatory, working on the 40-foot telescope and training users there. His primary interest is in radio is SETI. So here is Skip.
Okay. What the up down button is just. Thank you. Okay. Thank you all for coming to this. And yeah, I've had a lot of discussions with a lot of you over the years about these things. I'm going to just give a summary of everything I'm going to talk about, and then I'm going to try to go through it pretty quickly, just because I really like having questions. The around 2013, I started working with an interferometer of two 20-foot dishes on my farm in New Hampshire. And I started scanning various declinations 24 hours a day. And I was looking for communication pulses. So generally when I saw continuous signals, I would try to track them down. And one way or another, eventually I'd delete them because they were present in various directions. That led to seeing some strange things along the -7.6 declination arc. And I chose that to do searches here at Green Bank with the 40-foot telescope starting about 2017. Then at a SARA meeting here, Rich Russell and a few other members, we had a discussion, and the idea of doing simultaneous SETI with the 60-foot dish in Colorado and the 40-foot dish here, synchronized with GPS, came up, and we decided to do that. So we started that for about 3 years and ran that actually through the beginning of 2020, about 7 or 10 sessions. Rich ran the first one. Steve Plock then would set up my software and run it there. And then I would come here and run it here. And then everything was synchronized. Then I would go back home and get all the files and then look for simultaneous pulses on both dishes. Towards the last 2 or 3 of those observation runs, I was also running a 26-foot dish that I built on my farm, also synchronized, which I started up before I drove here. Then I went back home, and then I compared all 3 of the files together. So I'm going to talk about first 4 archive papers. I'm just going to summarize them very quickly that I wrote during the pandemic that covered all of the work that I had done up until January of 2020, the very beginning of the pandemic, which was our last simultaneous run, and then also covered work that I did on the 26-foot dish as a standalone method, scanning the sky, scanning, again, the -7.6 declination arc. So the idea is to look along that arc for as long as possible and for as many days as possible, and then just see if there's anything that looks like communication-like pulses. And if there's RFI, decide whether it should be excised and that sort of thing. Now, the most recent work that I've been doing is to build a new interferometer on my farm with smaller dishes, because the signal to noise ratios that I've been seeing on these strange pulses from one particular right ascension that I've been reporting in these papers is high enough that with a 2-element interferometer, and perhaps with some techniques of searching for communication signals, I might be able to be able to see them. And so I've been running that. It's only been calibrated since around mid-July. So, and I had a lot of construction work done at my house since then. So, and during that time. So I kind of don't have too much data. I only have a few weeks of data, recent data, recent data is telling me there is something strange at this 5.25 hour right ascension. However, it's way, way, way too early to say anything about that because there's so many other explanations for things. And I've mentioned this in another talk. I'm a huge proponent of which Karl Popper teaches, which is to try to refute as best as possible all of the alternate hypotheses before saying anything about whether there's proof to the hypothesis of the explanation that this is extraterrestrial. So I'm nowhere near making any claims whatsoever about extraterrestrial explanations for this. So spacebar. Is it on presentation? I see. It's kind of maybe it's a page. Is it a page down thing? So maybe it's is it a down arrow? Does down arrow work? Okay. I'll scroll this down. Okay. So yeah, that's great. Yeah. Oh. Okay, great. Okay. So I've summarized this. In the pictures, these are the two dishes, and then there's the dish over in New Hampshire. And what I do is I store at each site locally for generally 48 hours would be a run at each site. So we do 48 hours here, 48 hours there. Steve and I or Rich, we would synchronize via landline telephones to start the software at a particular time, verify that the scrolling is correct and that the time synchronization has occurred with the GPS clocks. The frequency is also calibrated because we have to correct for Doppler for the two sites. So we have to know that we're in a bin of the FFT. So what I do is I do FFTs in a 3.7 hertz bandwidth at a quarter second. And I'm not looking for continuous signals at one frequency. I'm looking for pulses that are communication-like pulses that have a bandwidth of 3.7 hertz and a duration of about a quarter second. In other words, they're Shannon efficient pulses, which are then that comprise a set of pulses that maybe have other characteristics, such as very close frequency spacing, very close time spacing, along with that pulse that say is first seen, it exceeds the signal to noise ratio. And then the presence of those pulse pairs and their polarizations becomes something that can be used with statistical analysis to say, okay, this isn't noise. So the first hypothesis is this is all caused by noise. And anything we see that is a simultaneous pulse on these antennas is going to be noise. And the idea is to refute that hypothesis mentioned earlier, is to refute the noise hypothesis. So the first paper goes into that, and I'll show what happened with, why isn't it scrolling? Do I use the mouse? Okay. Yeah, I guess I should use the mouse. Okay, I'll use the mouse to scroll. So these are from the first archive paper, and this started my interest in 5.25 hours right ascension. And it turned out along the -7.6 declination arc, I had an interest in the 4.25 hour declination or right ascension direction. Sorry, right ascension direction. And these 2 days of observations of a total of 48 hours and then 48 hours led me to say, I think I'd rather be paying attention to plus or minus a few hours or maybe even a full day around the 5.25 hour right ascension direction. And what happened was on August 15th and 16th of 2018, we saw high signal to noise ratios present on both antennas. Now, the upper table is the results of the highest signal to noise ratio seen in 48 hours of scanning the minus 7.6 declination arc on the two dishes. And it reports the frequencies, the offsets between the frequencies after Doppler correction, and the modified Julian dates. I just wanted to verify. So I make sure that these are simultaneous pulses by posting the data that came out when the event occurred, let's say. So those are the 5 highest signal to noise ratios that occurred during 24 hours or during 48 hours. They're the right ascensions posted on the left during the 48 hours that occurred. The second table has the highest 1, 2, 3, 4, 5, 6, 7, the highest 7 with a different delta F center. So for whatever reason, and I can't say, I could not find things at 0 hertz. So this is sometimes what happens in an experiment. It's got some errors into it for some reason. There's something that's been done wrong. Now, so this may be invalid data, but it turns out that if you pick a different frequency range for the Doppler shift, 2 of the highest 1, 2, 3, 4, 5, 6, 7 pulses seen on both dishes in the August 15th, 16th happen to be on the same or within that range of Doppler shift. So this got my attention because even if we say we're a little bit off in frequency, we would say if this is a noise hypothesis, well, then let's multiply that number by 5 or 10 because there's many other possible offsets in frequency. And could noise explain this, especially given that we've gotten a number 1 and a number 3 on a previous run. So this led to saying, 4 out of the top 10, it turns out, because these 2 are higher than the lower 2 of the first thing. The highest 4 out of, I think it's 10, it's 5 and saying something like this, are in the same 0.3 right ascension hour window out of 24 hours. So this is a fairly significant statistical event. And it's led me to continue looking in this direction and comparing this right ascension direction to others. So these are the preprint papers that I submitted to arXiv. The first one, I'm not going to go over them, but there's abstracts. The abstracts are contained. And you can just type these in and get the full papers. The first one describes a communication system together with the methodology used for this first set of tables above. The second one goes into all the radio, well, not all, but as many as I can had implemented in the software of radio interference rejection mechanisms. So these were excising techniques that I was using in the software. The third one is based on looking for symbol repetition. In other words, delta T, delta F, delta time, delta frequency offsets in time and frequency of the signals measured on the 26-foot dish in New Hampshire. And that was during the pandemic, which prevented my coming to Green Bank. The 40-foot was not being used in. And the last paper deals with quantization, looking for, are there any quantizations on frequency and time? Are the symbols separated, these strange simultaneous pulses, are they separated in time by a consistent value, which would give someone the ability to begin trying to decode whatever kind of communication signals are present. So, and also, and now I should say, and quantized as well. In other words, it's 1 times a particular delta F, 2 times a particular delta F. So my brother made up this wonderful, he designed this wonderful device which illuminates from below. And it the location that that I look in and I compare to other directions is just above the star Rigel. And so he made my dish there, pointing up there with my call sign. I'm not claiming there's anything interesting in that, but that happens to be the nearest star that's within this window, approximately 1 degree by 1 degree of range based on the 40-foot and the 60-foot dish. So I'm not claiming obviously anything's there, but there was a star there, a red dwarf. Okay. So so I've kind of had to struggle with, well, what am I assuming here? Well, I'm assuming quite a lot of things, really, and so I just want to point those out. Do we have to just say, for even wasting any time on this, first of all, could signals be beamed to us? And the answer to that is yes. I mean, Project Cyclops shows it. Then you have to question, based on the Drake equation, does it make sense? But I'm just assuming that. How far away might these signals be? Well, in order for the small antennas that I'm using to be practical, I have to say that they're probably, with what the technologies that we know for transmitters, probably need to be within about 100 light years. So I'm just saying, look out that. Then the other idea is, are there any transmitters overall in the galaxy to make repeaters useful? Well, maybe there's a possibility that repeaters are being used. Maybe some of these repeaters are from a civilization that isn't living in that area. And the idea is maybe there are transmitters that are closer than actual civilizations existing. And then what would we do for a receiver? So, there's a general rule that if you haven't looked for something yet, but you can predict approximately a guess as to the signal to noise ratio that you can get with a particular aperture, the idea is to use the smallest aperture possible to get a signal to noise ratio that gives you statistical significance to the discovery you're making. And that's a basic thing about all searching for things, is you look for the widest possible range first and then narrow it in later. So that leads to the idea that smaller dishes can be used because they have wider beam widths and they look instantaneously at more of the sky. And then the question is, does something show up, or does it all fit the noise hypothesis? If it all fits the noise hypothesis, then we use bigger dishes and it takes longer to scan the sky for those signals. So the system that I've built is quite small, and I'm doing that on purpose because I'm trying to get to the noise hypothesis, but it's running into some problems. So what should the receiver be? So again, I said, scan the sky as fast as possible. I'm taking advantage of advanced computing systems, multi-core processors and things to run lots and lots of FFTs simultaneously. And also realize that cost of aperture, which this is a very old number from Project Cyclops, but I think it's still in the ballpark, that the cost of the aperture increases dramatically. And that leads to the idea that, try to use low aperture, get a statistical significance out of it, and speed up the whole search process. And then I'm making a gigantic assumption, which is that I'm only really looking for these delta T, delta F polarized pulse pairs. So I take cross polarized pulses and I say, wow, it's right hand and it's left hand. It's a kilohertz apart. It's a second apart. Those two pulses are statistically significant. We can do the statistics of seeing two close tones close together in noise at a high signal noise ratio. And in my papers, I discuss all those probabilities and how they apply to the experiments that I'm running. And that's a huge assumption, but to me, I feel pretty comfortable with it because it allows me to test the noise hypothesis with mathematics without having to deal with RFI. To a large extent, I can excise everything I see. So basically, anytime I see a continuous signal that falls across the right ascension window adequately, I just reject that 1 kilohertz band. So there are about 40 bands on my new interferometer that I just excise the data for with kilohertz bandwidth out of 50 megahertz. And I didn't mention that, but I run a 50 megahertz bandwidth from around 1400 to around 1450 megahertz. 3.7 hertz bands, quarter second FFTs. Okay. And then now, the big difference now with the system that I'm doing is I'm working to measure the angle of arrival. That's my goal, is to eventually determine within the uncertainty window that I have from previous tests and from the new tests that I'm doing with a wider beam width, determine where in that window these pulses are coming from, if they're coming from the sky. If they're coming from RFI, they might fill up the whole window of some sort, which means perhaps they're not celestial. Then that leads me to say, okay, how do I do that? Well, I can measure the phase across an interferometer. And that's what this paper is basically about. It's taken me a while to get to it. Okay, so the idea is to calibrate a dish. This drawing is amazingly like yours, Rich. And basically, we just measure the phase between the two elements after calibrating as much as we can. And that gives us an angle offset from the perpendicular of the baseline between the two phase centers of the dish. And this is a pretty standard method to just for radio direction finding, is to use two antennas and measure the phase across it. So this is the two-element interferometer that I have on my farm. There's an east element and a west element. And over in the corner, up sort of towards the left, there's a whole bunch of dish pedals there. These are made from three 3-meter dishes that I used to have that are 10 gigahertz fiberglass dishes. And I take 2 pedals from each dish, total of 8 pedals, and build a offset fed dish out of it. And then I add some mesh to the outside of it to reduce the noise up in the upper parts. So there's a little bit of mesh. I got a few other pictures of this coming up. And these are separated by about 23 feet. And I can build about 12 of them with the dishes that I have. And I can place them over about 11 acres of property. And this area here is surrounded by dense forest. So, and it's about 600 feet in the minimum direction to the nearest house. So in some distances, it's very, very far. There's only a few houses in this neighborhood. So the dishes are built by putting the surfaces on hand trucks, which coincidentally I had for a different project. I bought a bunch of them. So I have a bunch of those on the farm too, but I didn't use them for the other project. But this one, I put the dish into the hand truck, and then I build a frame out of super strut underneath it so that I can rotate the hand strut with additional wheels that you can see up there pointing, that rotate in azimuth. And then the hand truck itself, the main axle of the hand truck becomes the axis for elevation. So, and I installed 2 rotary angle sensors. One is a gravity sensor, and it's mounted to the hand truck. So its gravity reports back the azimuth back to the house. The other one is a rotary angle sensor, and it's located above the axle and then coupled down into a ground pipe that goes down below it, so that the axle rotation gives me azimuth in the house. And that turns out to be really important, because in interferometers, you'd like to get things within less than a beam width of the antenna. And these are about 9-degree beam widths. The feeds are 2 linear polarized composite elements made up of folded dipoles, 4 folded dipoles in a square. It's a pretty common way to get vertical and horizontal polarization without having to deal with dipoles that are coming to a center point where the feed has to occur, because you can bring the feed lines down to a reflecting surface. And then those are combined to create 2 circular polarizations. And I bring circular into the house. And then LNAs are located up in those boxes. And the feed was separately checked. I separately checked it to try to ensure the illumination. And since then, I found that there is a little bit of spillover. And so I placed some mesh material around it. It's temporary, but I plan to do a little bit of aperture increasing to increase the efficiency and also decrease, or slightly, and also decrease the noise a little bit. So what I'm doing here is running 2 simultaneous things at the same time. I'm running both a complex cross correlator in order to do wideband cross correlation interferometry to measure astronomical objects, to determine their direction and their phase. At the same time, I'm running FFTs that can give me individual 3.7 hertz bin receivers, around 16 million of them per dish, which I can then use to compare the SNRs for each bin, and then post those to a file. Now, the nice thing about having the complex conjugate multiply, the complex cross correlation, is that if an event occurs at some point and it's broadband, I can get an output out of the complex cross correlator at that particular time, and I can get a phase and a magnitude on it. And if whatever I'm looking at happens to be something that's a burst of some sort, that's very wideband and high energy, it'll show up on that integration. At the same time, though, if it's an extremely narrow band event, which only involves a few tones, let's say that only a few tones are present in the waveform, which provides really good statistical significance in a measurement, and it's relatively low energy, and it can meet close to Shannon's limit, assuming that it's using its bandwidth, its full amount of bandwidth eventually. Although for discovery purposes, you put the pulses closer together. And I explained this in the various papers that I wrote. So this was a calibration test that I did with the sun. So the reason there are discontinuities in the graphs are that I steered the dishes during the test to follow the sun across the sky. And so the top graph is the total continuum power. So I measure the continuum power, and I need to do that in 1 kilohertz bands because I need to get an average noise level so I can do a signal to noise ratio calculation. So that falls out automatically from the test. And then down below is the phase difference, and this is the cross correlator phase difference. So these are actually from two separate processes that are producing this. One is broadband continuum. The other one is cross correlation phase. Now, so I did an experiment here where I ran these phase wiggles that go from plus and minus pi here that I can use to compare the calculated amount of phase shift that should occur as the sun goes across the baseline to the measured number of cycles. And there was like 8.107 cycles of 2 pi across the interferometer measured. And I calculated, so the calculation and the measured values came out quite close if I take into account the astronomical considerations of the sun going across it. So this basically told me that, okay, I've got the measurement of my baseline and pretty carefully, and using those measurements, I came out with something just to say that things seem to be working. Now, the reason there's double lines over there is because I also do an FFT after the first quarter second FFT. And that set of FFTs that's running a quarter second later is being done on raw data that's captured over a second. So to prove that my total time window of a second of captured data is valid, I do 2 FFTs. I do one a quarter second later. Turns out the second line is the second FFT. And when that deviates, that tells me that something might be drifting across a 1 second interval. And my second quarter second has a little bit of a phase shift. So that's something I need to track down, and I haven't done that yet. Right now, I'm just basing my calibration on the first quarter second. So this is a plot of the magnitude of the cross correlation as opposed to the continuum and the phase of the cross correlation as different discontinuities occur. This is a different solar scan on I believe it was a different day. And it turns out that when the signal to noise ratio gets fairly low on the magnitude of the cross correlation up above, you can see, of the sun, the phase takes some discontinuities right there. And that's kind of expected, that if you get down to low signal to noise ratio on the sun, that there's going to be some discontinuities. And you can also see here that there's the double line problem again, because the other quarter second. Now, what happened is over time, there's something drifting very slowly, because then the lines lined up perfectly after a while. So there's something there I need to troubleshoot as to why there's a slow drift between the first FFT and the second FFT in the phase on that. And I'll have to fix that before I can do all the time windows, the quarter second time windows within the full 1 second capture that I do. Okay, so I was curious because when I started doing my solar work, and some of you may know, right around mid-June, M1 Crab Nebula was right practically close to the sun, and then it transited the sun within like a fraction of a degree, I think. I wanted to measure M1 separately because I could get it at the same without having to re-steer the elevation of the dish when I was doing solar measurements. So I waited for a little while, and I got it to the point where M1 was then quite far from the sun. And so the upper plot shows how the location of M1. Okay, great. Okay, thanks. Yeah. So M1 is located at where this arrow is, and then the sun is 22 degrees of sky angle off from it. Now, one of the things that happens is when you have two sources in a cross correlation at approximately equal amplitudes, they can null out. And those of you who did the mobile interferometer here years ago that we built going out at the 40-foot dish, remember that the idea was to look for the spacing between the Cygnus A lobes, and we were able to show that we could predict the angle spacing on the Cygnus A lobes. Now, I don't know if that's happening here, but there's a possibility that these nulls that are occurring are due to the two sources of cross correlation that are both present in the output, canceling each other out. Now, you can't get cancellation on a complex cross correlator if you only have one source, okay? But you do if you have more than one source, and that's what might be causing this. It might be also causing the phase to change because it's moving across the sky at a different rate. But I haven't looked at that enough to really know whether or not that's correct. So what's happened is that this situation right now is I've been testing the elements. I've been running them for only about a month, except there was a bunch of RFI during that time frame. And it's running. It's not running right now. I turned it off, but I run it 24 hours a day. I get up in the morning. I look at the 4 to 8 hour right ascension range, and I look for statistical, let's say, outliers in the 5.1 to 5.4 right ascension direction, trying to refute the noise hypothesis. And at this point, I don't have any slides on this, but I am seeing when I look over 1 day, 2 days, 3 days, and especially when I look over for like 5 days, I'm seeing far more pulses in that 0.3 hour window than noise would predict. In other words, noise should distribute them across all 0.3 hour windows within the 4 to 8 hour range. However, there are so many possible explanations for what could be going wrong that I really can't make any conclusion. It's way too early to discuss that data. Now I'm working to figure out what to do with the next element, and I got two wild ideas. My time is almost up. Is that right? Okay, so I'll just finish. Two wild ideas, which we could talk about in the Drake Lounge. That'd be fun because Wolfgang showed me this wonderful idea with a trailer, and I thought about it. I have a couple of cargo trailers, and I could probably do this. Is I could build one of the next element inside my cargo trailer and wheel it out of the cargo trailer down a ramp and go camp somewhere, 20, 30, 50 miles away or whatever. Camp for 2 days at a park, nice park where there's nobody else going. Maybe pick a day when the weather's bad or something like that, and just run it and keep my other one running back at home. Okay, that's one option. The other option is I could build, or I could do both, build another element and put it behind some local trees. Another one is I could build it and put it around some trees that are very, very far away on my farm and run fiber optic cable to it. I already run fiber to the 26-foot dish, so I could build up some more fiber optic systems to run to the distant one. So those are all ideas. And the idea is to get rid of the local interference first. And depending on how far I drive, get rid of the airplanes and get rid of potentially even near Earth satellites, perhaps some, depending on how far I drive. So let's see. I think that's it. Okay. Yeah. Thank you very much. Thank you. Yes.
So what are the real RFIs?
Oh my goodness. I have so many stories to tell on that are really, I've had a lot of fun tracking down RFI. I've tracked down RFI here at Green Bank using when it's during a maintenance interval, I can go around with my spectrum analyzer antenna, and I found one that's an optical receiver that runs at 2.048. By the way, if you see 2.048 megahertz comb on the 20 meter, okay, there's a chance it's coming from the box that's down in the pedestal of the 20 meter. Now, that was years ago, so it's perhaps been replaced because I told them, and then maybe they replaced it. But on my farm, I do all kinds of fun things looking for RFI. It's a kick. Yeah. And what are they, like a clock radio? But that's a long story I could talk about. There's clock radios all over the country. They're all synced to the 60 cycle line. So when you see signals that are sitting within one bin, but they're fluctuating just ever so slightly, and you go, my goodness, that must be a stable oscillator somewhere. Is there somebody transmitting it out there from a satellite or something else? But you'll find it all over the country. And I traveled the country, part of it with my brother, used 5 telescopes at like 3 observatories to finally find out that it's a clock radio chipset that's locked to the 60 cycles. It's at 1411.283 megahertz. If you see anything at 1411.283 megahertz, it's a clock radio chipset.
Any difference on that type of thing in the state of Texas, because their power grid is isolated from the rest of the country?
Good question. Yeah.
60 hertz, although 60 hertz isn't necessarily phase lock.
Yeah, good question. They add, my knowledge is they put pulses in to get the time back, but they just do it whenever, like there's been an outage for a little while in an area, and then they inject additional pulses. So that's why electric clocks they're on time. Yeah. Oh, and I forgot to show you all this, but since we've had so much discussion about interferometers here at this conference, I want to tell you that this book, Thompson, Moran, Swenson, TMS, this is the book. This is like the Krauss Blue radio astronomy book for interferometry. It's very thick. But if you have any questions about interferometry in the Drake Lounge or whatever else, I'll see if I can look it up in this book, because this book is, yeah, it's a little bit spendy, but you could save probably enough money by buying this book and reading what's in it than buying whatever hardware you plan to buy for an interferometer. It might save you the cost of buying 3 or 4 dongles or something like that. I don't know. So it's probably a good thing to have. Yeah, I found. Yeah, any more questions, or any more questions from online? Okay, yes. Okay.